Namaste, tutor. I'm really looking forward to today's deep dive. We're tackling a concept that seems simple on the surface, but it's everywhere in chemistry, right? From why our cold drinks lose their fizz to how oxygen actually gets into our blood cells. What's the big topic for us today?
Namaste, you've set the stage perfectly. Today, we're diving deep into the fascinating world of equilibrium. And you're right, it's not just some theoretical concept you'll see in your Class 11 textbooks. It's fundamental to countless biological, environmental, and, well, industrial processes too. And crucially, for all you preparing for competitive exams like JEE and NEET, mastering equilibrium can give you a significant edge. It's a consistently high-scoring topic.
So equilibrium. Okay, for me, that word usually brings to mind something static, like a perfectly balanced weighing scale where nothing is moving. Is that how we should think about it in chemistry?
That's a very common misconception, and it's really vital we clear that up right away. In chemistry, equilibrium is anything but static. Instead, think of it as a dynamic balance. It's a state where opposing processes are happening simultaneously, but, and this is key, at exactly equal rates. Imagine a busy escalator. People are constantly going up, right? And at the same rate, new people are stepping onto the escalator going down. The number of people on the escalator might seem constant from afar, but there's a lot of hidden activity.
Oh, okay. That's a much more active image. Can you give me a classic example, maybe from everyday life, that shows this dynamic nature?
Absolutely. Let's take a sealed bottle of water at room temperature. Initially, water evaporates, it turns into vapor, the pressure inside the bottle starts to build up. That's the evaporation rate. But as more water vapor molecules accumulate in the space above the liquid, they start colliding with the liquid surface and returning to the liquid phase. That process is condensation. As time passes, the rate of this condensation gradually increases.
And eventually, what happens to those rates? Do they become equal?
Exactly. Eventually, the rate at which water molecules leave the liquid phase becomes precisely equal to the rate at which they return from the vapor phase. At this point, the system has reached equilibrium, the vapor pressure inside the container becomes constant, and the macroscopic properties, things you can see like the amount of liquid or vapor, they appear stable. But remember, at the molecular level, evaporation and condensation are still furiously happening. They're just balancing each other out perfectly. This dynamic continuous activity is why we use those double half arrows, like H0 liquid, arrows, H0 vapor, H0L equals HHO vape. It signifies that both forward and reverse processes are constantly in play. And the mixture of substances present at this point, we simply call that an equilibrium mixture. It's not a reaction that has just stopped. It's one that has found its perfect dynamic balance.
So it's like a constant invisible dance happening all the time. Does this dynamic equilibrium apply to other physical processes too, not just evaporation?
Oh, certainly. This fundamental principle extends to many everyday physical changes. Let's look at a few key examples for your exams. First, consider solid-liquid equilibrium. Think melting and freezing. If you put ice cubes into a thermos flask with water precisely at 0 degrees Celsius or 273 Kelvin and normal atmospheric pressure, you'll observe something interesting. The total amount of ice and water remains constant. But if you could zoom right in to the boundary between the ice and the liquid, you'd see a flurry of activity. Water molecules are constantly moving from the liquid onto the ice surface, freezing. And simultaneously, ice molecules are escaping back into the liquid, melting. At the normal melting or freezing point, these two opposing rates are exactly equal. So while your ice cube isn't visibly shrinking or growing, it's still dynamically interacting with the water all around it.
Fascinating. And what about when you boil water? That's also a liquid-vapor equilibrium, isn't it?
Correct. Think about liquid-vapor equilibrium, maybe in a closed system like a pressure cooker. As water heats up, more and more molecules gain enough energy to escape into the vapor phase. This increases the vapor pressure inside. Eventually, the rate of evaporation matches the rate of condensation. At this point, the pressure inside stabilizes. We call this the equilibrium vapor pressure. What's interesting and important for exams is that this equilibrium vapor pressure increases significantly with temperature. Why? Because more molecules have the energy to escape the liquid phase. This explains why liquids with a high vapor pressure at a given temperature, like say methyl alcohol or acetone, are very volatile. They evaporate easily and consequently have lower boiling points compared to water, and that standard atmospheric pressure we often talk about. The normal boiling point is defined as the temperature at which a liquid's equilibrium vapor pressure exactly equals the external atmospheric pressure, usually taken as 1.013 bar.
So that's why water boils faster, at a lower temperature in places like Shimla or Leh, because the air pressure is lower up there.
Exactly. Lower atmospheric pressure means the water's vapor pressure needs to reach a lower value to equal it, which happens at a lower temperature. But remember, in an open pan, you don't really reach this equilibrium because the vapor molecules just escape into the air. It needs to be a closed system.
Okay, got it. I've also seen solid iodine, turning directly into a topal gas. Is that a type of equilibrium too?
Excellent observation. That's a perfect example of solid vapor equilibrium, which we also call sublimation. If you place some solid iodine crystals in a closed container, you'll start seeing that characteristic violet vapor forming. The color intensity will increase for a while, and then it becomes constant. This signifies that the solid iodine is subliming into vapor, and at the same rate, the iodine vapor is condensing or depositing back into the solid form. The rates of these opposing processes become equal at equilibrium. Camphor and ammonium chloride show similar behavior.
Right. And dissolving things like sugar in my chai, that must also be some form of equilibrium, yes. Because you can only dissolve so much sugar before it just sits at the bottom.
Precisely. That's equilibrium involving dissolution. When you have a saturated sugar solution, even though it looks like no more sugar is dissolving, there's actually a dynamic equilibrium happening. Sugar molecules are continuously dissolving from the solid crystals into the solution, and at the very same time, sugar molecules are crystallizing out of the solution, depositing back onto the solid. The rates are equal. We actually know this is dynamic because of experiments using radioactive tracers. If you add a tiny bit of radioactive sugar to a saturated solution after some time, you'll find radioactivity in both the solid sugar at the bottom and in the dissolved sugar, proving there's a continuous exchange happening.
And soda water, when it goes flat after opening, that must be a gas-liquid equilibrium changing, right?
Spot on. The fizz in your soda water is a textbook illustration of gas-liquid equilibrium. Inside a sealed soda bottle, carbon dioxide gas is dissolved in the liquid, kept under high pressure. This specific equilibrium is governed by Henry's law. For your exams, Henry's law essentially states that the mass, or amount of gas dissolved in a liquid, is directly proportional to the partial pressure of that gas above the liquid. It also depends on temperature. Solubility usually decreases as temperature increases for gases. So when you open the bottle, the pressure of co-Euro gas above the liquid suddenly drops to the much lower atmospheric pressure. According to Henry's law, the solubility of co-Euros decreases drastically. This causes the dissolved gas to rapidly escape as bubbles until a new equilibrium is established, one with much less co-Euros dissolved. That's why your soda goes flat if you leave it open.
So, okay, summarizing these physical equilibria.
Yeah.
They all seem to happen in closed systems, right? At a specific temperature.
Yes.
And they involve opposing processes happening at equal rates.
Correct.
Which leads to constant measurable properties like pressure or concentration. And each type is defined by some specific constant value like vapor pressure or solubility.
Exactly right. That's a perfect summary. And now, let's take this core understanding of dynamic equilibrium and apply it to where it gets really interesting for chemists. Chemical processes. When you mix chemical reactants in a closed vessel, they start reacting to form products. Initially, reactant concentrations decrease, product concentrations increase, but eventually, just like in physical systems, all these concentrations stabilize and become constant. This state is chemical equilibrium, and crucially, it's just as dynamic as the physical ones. It's the point where the rate of the forward reaction, reactants turning into products, becomes exactly equal to the rate of the reverse reaction, products turning back into reactants.
But how do we know it's dynamic? Like, really know? Could the reaction just stop once it reaches that balance? That seems simpler.
That's a brilliant question, and it was a real puzzle for early chemists. The definitive proof of the dynamic nature of chemical equilibrium comes from some clever experiments using isotopes. Let's consider the famous Haber process for synthesizing ammonia. Ng plus 3H equals 2NHG. This reaction is vital for making fertilizers. It reaches an equilibrium where the concentrations of nitrogen, hydrogen, and ammonia stay constant. Now, to prove it's dynamic, imagine we do something slightly different. We perform the Haber process using deuterium euro, which is just a heavier isotope of hydrogen, so we form Nd euro instead of NHE. You let this reach equilibrium, so you have a mixture of N euro and NDU. Now, here's the clever part. We take this equilibrium mixture and carefully combine it with a different equilibrium mixture, one made with ordinary hydrogen containing N euro, regular HO, and NH.
Okay, so you're mixing two separate systems that are already at their own equilibrium points.
Precisely. Now, if the reactions had simply stopped dead once equilibrium was reached in each separate flask, what would you expect to find when you mix them?
I guess just the original molecules. N euros, NH is D and ND. Nothing new should form, right?
That would be the logical assumption if equilibrium were static. But when this combined mixture is analyzed, say using a mass spectrometer, which can distinguish between different masses, we find something surprising. We detect new species appearing, molecules like NHED, NHD, and even some HD molecules, hydrogen deuteride.
So the hydrogen and deuterium atoms are somehow swapping places or scrambling.
Yeah. Exactly. This scrambling of H and D atoms between different ammonia molecules and even forming HD can only happen if the forward reaction, forming ammonia, and the reverse reaction, breaking down ammonia, are continuously proceeding, even at equilibrium. These ongoing reactions allow atoms to be exchanged between molecules. This is really strong, conclusive evidence that chemical equilibrium is a truly dynamic process. The reactions never actually stop. They just perfectly balance each other out at equal rates. Another key takeaway for your exams is that equilibrium can be reached from either direction. Whether you start with only reactants, like N and H, or only products like NHs, as long as the overall number of nitrogen and hydrogen atoms in the container is the same, you will eventually arrive at the very same equilibrium mixture with the same final concentrations.
That's genuinely fascinating.
Ah,
So the reaction is constantly balancing itself. How do we quantify this balance then? I assume that's where the law of chemical equilibrium and this thing called the equilibrium constant come in.
you've hit the nail right on the head. This is where we move from the concept to the calculations, which are so important for JEE and NEET. The core question becomes, what's the mathematical relationship between the concentrations of reactants and products once equilibrium is established? Back in 1864, two Norwegian chemists, Goldberg and Wage, formulated what we now call the law of mass action, based on a lot of experimental work. The term mass action might sound a bit old-fashioned now. It basically referred to the active mass, or, as we'd say today, the concentration of a substance.
Okay, so how does this law translate into an actual equation, let's say, for a general reaction, like A moles of reactant, A plus B moles of B react reversibly to form C moles of C plus D moles of D?
Right, let's write that general reaction. AA plus BB equals CC plus DD. For this reaction, at equilibrium, the equilibrium constant, which we usually denote as Kc, is expressed as a ratio. It's the product of the equilibrium concentrations of the products, each raised to the power of its stoichiometric coefficient, divided by the product of the equilibrium concentrations of the reactants, each raised to the power of its stoichiometric coefficient. So the expression looks like this. Kc multiplied by den, all divided by n multiplied by ben. Remember, the square brackets A mean the molar concentration, moles per liter, of each species at equilibrium. The subscript C in Kc reminds us we're using concentrations, and those coefficients from your balanced chemical equation A, B, C, D become the powers or exponents in the S expression.
Okay, so for that reaction you mentioned earlier, Hg plus Ig to Hig, the Kc would be Hi squared divided by H times I.
Precisely. And the really powerful thing that Goldberg and Wage found, confirmed by countless experiments since, is that for any specific reaction at a given temperature, this ratio, once equilibrium is reached, always gives a constant value. It doesn't matter if you started with lots of H and I's or lots of Hi or some mixture. Once it settles into equilibrium, that Kc value is fixed for that temperature. That's the power of Kc.
Got it. What are some of the key properties of this Kc constant that I need to know for exams?
Excellent question. There are 5 critical points you absolutely must remember about Kc. First, Kc has a unique constant value for a particular reaction only at a given specific temperature. Change the temperature and Kc changes. Second, Kc is independent of the initial concentrations. It doesn't matter how you started the reaction. The final equilibrium ratio defined by Kensik will be the same at that constant temperature. Third, if you write the reaction in reverse, products becoming reactants, the equilibrium constant for that reverse reaction, let's call it Kc, is simply the inverse of the forward reactions constant. So Kc equals 1 Kc. Fourth, if you multiply the entire balanced chemical equation by some factor and say you double all the stoichiometric coefficients, the new equilibrium constant for that modified equation becomes the original Kc raised to the power of n. So if you double the equation, the new constant is Kcc. This means it's absolutely crucial to always specify the exact balanced chemical equation when you're quoting a Kc value, because its numerical value depends entirely on how the reaction equation is written. And fifth, related to the first point, Kant's only applies when the system is actually at equilibrium.
Okay, that makes sense, especially the part about needing the specific balanced equation. Let's try a typical problem. How would we calculate Kc if we're given the concentrations at equilibrium?
Good idea. Let's take a common scenario, the formation of ammonia again. N euro plus 3Hg equals 2NHG. Suppose at equilibrium, say at 500 Kelvin, we measure the concentrations and find N euro equals 1.5 to 10 notmolar, H euro equals 3.0 or 10 onmolar, and NHAs is 1.2 by 10 onmolar. How would we find Kc?
Okay. First, I'd write the Kc expression. That would be NH euro squared on top divided by N euro times H euro cubed on the bottom. Then I just plug in the numbers they gave me.
That's exactly the correct approach. So Kc equals 1.2 times 10 to the power of minus 2 squared divided by 1.5 times 10 to the power of minus 2 multiplied by 3.0 times 10 to the power of minus 2. Now, you need to be careful with the calculation, especially the exponents. When you work it out, you should find Kc comes out to be about 3.55 10 to 10 times errors. And the main skill here is setting up the expression correctly based on the balanced equation and then substituting the equilibrium values accurately.
Understood. Now, for reactions involving gases, I've heard we sometimes use partial pressures instead of concentrations. Is that right? What's that constant called?
Yes, you're referring to take-me. When all reactants and products are in the gaseous phase, what we call a homogeneous gaseous equilibrium, it's often more convenient and sometimes experimentally easier to work with their partial pressures instead of molar concentrations. The connection comes directly from the ideal gas equation, PV equals nRT. If you rearrange it, you get P NVRT. Since NV is just molar concentration, you can see that partial pressure, P, is directly proportional to concentration gas at a constant temperature. So for our hydrogen iodide reaction, Hg plus I euro 2HIg, just as we wrote Kp using concentrations, we can write Kp using partial pressures. Kp partial pressure Hi suppose divided by partial pressure Bayer and multiplied by partial pressure of I euro. We often write partial pressure as sub I sub H2 sub, etc. Interestingly, for this specific reaction, H euro plus I euro equal to Hi, it turns out that Kp is actually numerically equal to Kp. Why? Because the total number of moles of gaseous products, 2 moles of Hi, is equal to the total number of moles of gaseous reactants. 1 mole H euros plus 1 mole I euros is 2 moles.
But if the number of moles of gas changes during the reaction, then Kp and Kpc won't be the same.
Exactly right, and that's usually the case. There's a general relationship between Kpacag, which is extremely important for your exams. You must know this formula. Kp equals Kc RTM. Let's break that down. R is the ideal gas constant. You need to use the value that matches your units for pressure and volume, often 0.0831 bar liter per mole, Kelvin if pressure is in bars. T is the absolute temperature in Kelvin, and the crucial term is delta N. T is the change in the total number of moles of gaseous products minus the total number of moles of gaseous reactants, taken directly from the balanced chemical equation. If A is 0, like in the HEI example, then RT raised to the power of 0 is just 1, so Kp equals Kc. But if N is positive or negative, Kp and Kp will have different values.
Okay, let's try applying this. Say, for the reaction 2NOG plus KOG plus PlaHG, we're given that KEC is 3.75 or 10 PA at a temperature of 1069 Kelvin. How would we find Kp?
All right, first step, find Kp for this reaction. Look at the balanced equation. How many moles of gaseous products are there?
2 moles of NO plus 1 mole of CO, so that's 3 moles of gas on the product side.
Good, and on the reactant side?
Just 2 moles of NaCl gas.
Perfect. So moles of gaseous products, moles of gaseous reactants equal 3,2 equals 1. Now we use the formula Kp, EC, RT. We just plug in the values. Kp 3.75 dies 10 euro, multiplied by 0.0831 times 169 raised to the power of 1. Calculate the value inside the bracket first. 0.0831, 1069 is about 88.8. Then multiply by Kp, 3.75, 10 euro, 88.8. When you do the multiplication, you'll find Kp is approximately 0.033. This type of direct conversion between Ksc and Kp using own is a very standard problem type in competitive exams.
Okay, that clarifies the Kp and Kpon relationship. So far, we've talked about reactions where everything is in the same phase, homogeneous equilibria, they call them. But what about reactions involving different phases, like solids reacting with gases or liquids involved? How do we handle those?
Excellent question. Those are called heterogeneous equilibria. A system involving reactants and products in more than one phase, for example, a solid decomposing to produce a gas in another solid, or a solid dissolving in a liquid, is a heterogeneous equilibrium. A classic example is the thermal decomposition of solid calcium carbonate at limestone, CaCoA CaOs plus KOR. Here you clearly have two different solid conses, CaCO and CaO, and one gas phase.
Right. And how does having solids or liquids involved change the way we write the equilibrium constant expression? Does it make it more complicated?
Actually, it makes it simpler. This is a very important point to grasp for your exams. The key principle is that the concentration, or more accurately the activity, of a pure solid or a pure liquid is considered to be constant. It doesn't really depend on how much of the solid or liquid you have present, as long as some is there. Because their concentrations are constant, we effectively incorporate them into the value of the equilibrium constant itself. So for the CaCO decomposition, CaCOS plus COU. If we were to write the full CaCO expression naively, it might look like COS, COG, CaCOs. But since the concentrations of the pure solids, COS and CaCOS, are constant, we combine them with the original K value to define a new simplified equilibrium constant. This simplified constant, let's call it CaCO, ends up being just the concentration of the gaseous product, K or C, CaCO EC, or if we're using pressures for the gas, the expression for CaCO becomes simply CaCO T equals PCO, the partial pressure of carbon dioxide.
Wow, okay. So as long as there's some solid CaCO in, some solid CaO present, the pressure of K or O's gas in equilibrium with them will be constant at a given temperature, no matter if I have a tiny amount or a huge pile of the solids.
Exactly. That's the crucial concept. The pure solids or pure liquids must be present for the equilibrium to exist, but their concentration terms do not appear explicitly in the final simplified K expression that you use for calculations. Another quick example, for the reaction NeS plus 4COD, which is used in nickel purification, the nickel is a solid. So the K-side expression would be KCOG, the solid Ne term is excluded. Same for KPO.
That simplifies things nicely. What about the units of the equilibrium constant then? I've noticed sometimes Kc or Kc values are given with units like mol, or bar, but sometimes they're just numbers. How do we know?
That's a good point about units. The units of Kc or Kp depend directly on the stoichiometry of the reaction, specifically on that value of Kb we calculated earlier, the change in moles of gas for Kp, or overall moles for Kc if including solutes. If Kb is 0, like in our Hg plus Ig plus 2HIg example, then all the concentration or pressure units in the Kc or Kp expression cancel out perfectly, and the equilibrium constant is dimensionless. It has no units. However, if Kt is not 0, the units won't completely cancel. For example, in N-Euros, 2HEO11, here Kc would have units of mol, and Kp would have units of bar. Sometimes, particularly in more advanced thermodynamics, concentrations and pressures are expressed as ratios relative to a standard state, like 1m or 1 bar, which makes the equilibrium constants formally dimensionless. But for most JEE and NEET level calculations, you should generally track the units and include them unless Un is 0 and they clearly cancel out.
Okay, let's try a problem that combines heterogeneous equilibrium and Kp calculations. Let's say we have the reaction COG plus CS, 2COG. The kBp value is given as 3.0 at 1000 Kelvin. If we start with some pure graphite, solid carbon, and an initial partial pressure of TCROs of 0.48 bar and no CO initially, how do we find the equilibrium partial pressures of CO and Ka? Okay, this is a classic heterogeneous equilibrium problem. First, what do we remember about the solid carbon? We excluded from the Kp expression.
Exactly. So the Kp expression is just Kp, H2O, PF, PCO. Now let's set up an ICE table using partial pressures. Reaction. KOU plus CS to COG. I, initial pressures. PCOU is 1.48 bar. PCO is 0 bar. Graphite is present, but doesn't go in the table numbers. C, change in pressures. Let X be the amount of key or pressure that reacts. According to the stoichiometry, for every X bar of KO that reacts, a 2X bar of CO is formed. So the change for CO is minus X, and the change for CO is plus 2X. E, equilibrium pressures. PCO up to 0 plus 2X equals 2X bar. Yeah, substitute these equilibrium pressures into our Kp expression. Kp, OYO, PCO, EQX, ferros. So 3.0 if you QX back to 0.48.
Okay, so we need to solve this equation for X. It looks like a quadratic.
It does. Expand it out. 3.0 is by X to X equals 2X equals 4 back zero. This gives 1.44, 3.0X equals 4 back zero. Rearranging into standard quadratic form. 4 back zero plus 3.0 by 1.44 equals 0. Now you'd use the quadratic formula to solve for X. Remember, X equals minus B, S squared, that's B chord CO2A. Here, F4, B3, C-1.44. You'll get two possible values for X. One will likely be negative, which doesn't make physical sense for a pressure change here. You need to choose the positive root. When you calculate it, the positive root comes out to be approximately X 0.33 bar. Final step, substitute this value of x back to find the actual equilibrium partial pressures. Equilibrium PCO x equals 2.33 equals 0.66 bar. Equilibrium PCO 0.48 x equals 0.48, 0.33.15 bar. This type of problem tests multiple skills, recognizing heterogeneous equilibrium, setting up the KP expression correctly, using the ICE table with partial pressures, and solving the resulting algebraic equation, often a quadratic. It's great practice.
That makes sense. So we've learned how to quantify equilibrium with these constants, Kc and Kp. What are the main practical applications of knowing these values? What can they actually tell us about a reaction?
Excellent question. Knowing the value of an equilibrium constant, Kc or Kp, is incredibly useful. It provides quantitative insight into chemical reactions. There are three main applications that are vital for your understanding and frequently tested in exams. First, the magnitude of K helps us predict the extent of a reaction. That is, how far does the reaction proceed towards products before it reaches equilibrium? Does it go almost completely or hardly at all? Second, if a system is not yet at equilibrium, we can predict the direction the reaction will shift to reach equilibrium. For this, we use a related quantity called the reaction quotient, Q. And third, perhaps most commonly in problems, we can use K to calculate the actual equilibrium concentrations, or partial pressures, of all the reactants and products given the initial conditions. Let's start with predicting the extent. The numerical value of Kc or Kp is a direct indicator of where the equilibrium lies. We can group reactions into three broad categories based on their K values. 1, if K is very large, say Kc 10 to 51 nanometer, this means the numerator in the K expression products is much larger than the denominator reactants. At equilibrium, the products greatly predominate. The reaction essentially proceeds almost to completion. Think about reactions like the combustion of hydrogen. 2Ag plus Og plus Og, its Kc is enormous, something like 2.4 A10 over at 500K. This tells you that virtually all the hydrogen and oxygen will react to form water. 2, if K is very small, say Kc 10O up. Now the denominator reactants is much larger than the numerator products. Reactants predominate at equilibrium. The reaction barely proceeds in the forward direction. A good example is the decomposition of water back into hydrogen and oxygen at room temperature. The Kc for that is minuscule, around 4.1 per 10 over O. This tells us that under these conditions, water is extremely stable and very little decomposes. Similarly, the formation of nitric oxide, NO, from N and O in the air at room temperature has a very small Kc, about 4.8 pet-Rg, meaning very little NO forms naturally. 3, if K is in an intermediate range, roughly between 10O and 10mg. In this case, neither reactants nor products are overwhelmingly favored. At equilibrium, you'll have appreciable, measurable concentrations of both reactants and products present in the mixture. The reaction is truly reversible in a practical sense. The classic example here is the formation of HI from H and R's, Hg plus I euro equals 2 Hig. Its Kc is around 57 at 700K, falling squarely in this intermediate range. Another is the decomposition of N euro into N euro, where Kc is about 4.64 by 10 R or more.
That's very helpful for getting a feel for how complete a reaction is likely to be. Now, what about predicting the direction? You mentioned the reaction quotient, Q. How does that work?
Right. Predicting the direction is where the reaction quotient Q comes in. Q, or Qc for concentrations, Qp for pressures, is calculated using the exact same mathematical expression as the equilibrium constant K. The crucial difference is that you plug in the concentrations or partial pressures that exist in the system at any given moment, which may or may not be equilibrium conditions.
Okay, so I calculate Q using the current concentrations. How does comparing that value to the known K tell me which way the reaction needs to shift?
It's a straightforward comparison, really, and it's based on the system trying to reach equilibrium where Q equal K. There are three possibilities. If QK, the current ratio of products to reactants is smaller than the equilibrium ratio. To reach equilibrium, the system needs to increase the products and decrease the reactants. Therefore, the net reaction will proceed in the forward direction, left to right. If QK, the current ratio of products to reactants is larger than the equilibrium ratio. To reach equilibrium, the system needs to decrease the products and increase the reactants. The net reaction will proceed in the reverse direction, right to left, if Q equal K. The system is already at equilibrium. The ratio matches the equilibrium constant, so there is no net change or shift occurring. Let's illustrate this quickly with the H euro plus I euro is 2HI reaction again. We know Kc equals 57.0 at 700. Now, imagine at some specific moment we measure the concentration concentrations and find H euro 0.10, I euro 0.20, and HI equaling 0.40 m. First, calculate QC using these concentrations. QC equals HIOOM, 8.0.10, and 8.0, 0.16, equals 8.0. Now compare QC to KC. We found QC equals 8.0, and we know KC equals 57.0. Since QC, 8.0, is much less than QC, 57.0, this system is not at equilibrium. To reach equilibrium, QC needs to increase. This requires forming more product HI and consuming reactants, H and OI. Therefore, the net reaction will proceed in the forward direction until QC eventually equals 57.0. This ability to predict the shift is a really powerful diagnostic tool for chemists and for solving exam questions.
That makes perfect sense. It's like checking if the system needs to move left or right to get to the target K value. Okay, and the third application you mentioned was actually calculating the equilibrium concentrations. This seems like the most common type of calculation problem. How do we approach those systematically?
Yes, calculating equilibrium concentration is a very frequent task in exams. The most reliable and structured way to tackle these problems is by using the ICE method. ICE stands for Initial, Change, Equilibrium. It provides a clear, step-by-step approach that works for almost all equilibrium calculation problems. Let's outline the steps. Step 1. Always start by writing down the correctly balanced chemical equation for the reaction. Step 2. Construct an ICE table directly below the equation. This table will have rows for initial, change, and equilibrium, and columns for each reactant and product. Fill in the I initial row with the starting concentrations or partial pressures of all species. Often, product concentrations start at 0, but not always. Determine the C change row. This represents how the concentrations change as the reaction proceeds towards equilibrium. You usually define a variable, typically X, to represent the change in concentration of one species based on the reaction's stoichiometry. Reactants will decrease, so their change is negative, like minus X or minus 2X, and products will increase, so their change is positive, like plus X or plus 3X. The coefficients from the balanced equation dictate the relative changes. Calculate the E equilibrium row by adding the change to the initial concentration for each species. So equilibrium equals initial plus change. The equilibrium concentrations will usually be expressed in terms of X, example 0.1X or 2X. Step 3, substitute these equilibrium concentrations, which are in terms of X, from the E row of your table into the correct equilibrium constant expression, Kc or Kp. Step 4, solve the resulting algebraic equation for X. This equation is often a quadratic equation, but sometimes it might be simpler, like taking a square root or even a cubic, though less common in introductory levels. You might need the quadratic formula. Importantly, you must choose the value of X that makes chemical sense. For instance, equilibrium concentrations cannot be negative, so if one root for X leads to that, you discard it. Step 5. Once you have the valid value for X, substitute it back into the expressions in the E row of your ICE table to calculate the final numerical equilibrium concentrations or partial pressures for all species. Step 6. This step is optional but highly recommended, especially during an exam if you have time. Check your answer. Plug the calculated equilibrium concentrations back into the Kc or Kp expression. The result should match or be very close to the given equilibrium constant value. This confirms your calculations are likely correct. Let's apply this to a typical JEE NEET style problem. Consider the reaction COG plus HERO plus Hg. Suppose Ka is 4.24 at 800 Kelvin. If we start with only CO and HO and their initial concentrations are both 0.0 m, how do we find the concentrations of all four gases at equilibrium?
Okay, I definitely start by setting up the ICE table for this one.
Let's do it together. Equation. COG plus HERO, COG plus HERO, HERO, COG plus HERO, I initial M. COO 0.10, HERO, HERO, C change M. Let X be the amount of CO that reacts. Since the stoichiometry is 1.1, if X moles of CO react, then X moles of HERO or HERO also react, and X moles of HERO also react, and X mole of HERO and X moles of HERO are formed. So changes are minus X for CO, and for HERO plus X for CO plus X for HERO, iso 0 is co-ROs, HR.1XX, co-XXX. Now, step 3, substitute these into the Kc expression. Kc, Furo, Eros, HC goes 2.1XX, Nulberg 1XX, and 1XX, X 0 and XX.
This one looks like we can just take the square root of both sides to avoid solving a full quadratic equation.
You noticed. That's a nice simplification that sometimes occurs when the exponents match on top and bottom. So take the square root of 4.24, which is about 2.059. Now the equation is x, 0.10x, is scale 2.059. Now solve for x. Multiply both sides by 0.1x, x equals 2.059. 0.1x equals 0.2059, x equals 0.059, x 0.059x. Rearrange to get all x terms on one side. X plus 2.059x equals 0.059, which means 3.059, x equals 0.067. Step 5. Find equilibrium concentrations. CO0 x in 0.01067, x is 0.10, x 0.0.0.067, x 0.033 m. This problem beautifully illustrates the power and structure of the ICE method for finding equilibrium concentrations. Mastering this technique, including the algebra involved, is absolutely essential for success in your competitive exams. Make sure you practice many such problems. That makes the ICE method very clear and systematic. Thank you. Now, could we switch gears a bit and connect equilibrium back to something more fundamental from thermodynamics? I remember learning about Gibbs free energy in Unit 5. How does that relate to equilibrium?
Excellent transition. Yes, the connection between Gibbs free energy, G, and equilibrium is profound and provides a thermodynamic basis for why equilibrium occurs. From thermodynamics, you'll recall that the change in Gibbs free energy, Gg, for a process at constant temperature and pressure tells us about its spontaneity. If Eg is negative, AgGO, the reaction is spontaneous in the forward direction as written. If Eg is positive, EGG, the forward reaction is non-spontaneous. Instead, the reverse reaction is spontaneous. The crucial point for equilibrium is when Eg equals 0. At this specific state, the reaction has reached equilibrium. There's no net driving force, no free energy available to push the reaction further in either the forward or reverse direction. The system is at its minimum free energy state under those conditions.
Okay, and isn't there a specific mathematical equation that links the standard Gibbs energy change, e.g. degrees, to the equilibrium constant, K? That seems like a really important connection.
Yes, there is, and it's one of the most powerful equations bridging thermodynamics and equilibrium. The fundamental relationship is Ag equals Ag plus RT ln Q. Let's unpack this. Ag is the Gibbs energy change under any conditions. Ag degrees is the standard Gibbs energy change, which applies when all reactants and products are in their standard states, typically 1 bar pressure for gases, 1 m concentration for solutes, pure solids, liquids. R is the ideal gas constant, T is the absolute temperature in Kelvin, and Q is the reaction quotient we just discussed, the ratio of products to reactants under the current non-equilibrium conditions. Now, think about what happens at equilibrium. At equilibrium, two things are true. The overall Gibbs energy change, Ag, becomes 0, and the reaction quotient Q becomes equal to the equilibrium constant K, Kc, or Kp. So let's substitute these conditions into the equation. 0 Eg degrees plus RT ln K. Rearranging this gives us the pivotal relationship you were asking about. Ag degrees equals RT ln K. This equation allows you to calculate the standard Gibbs energy change for a reaction if you know its equilibrium constant and vice versa. You can also express K in terms of A degrees by rearranging further. ln K includes Weich's G degree RT and then taking the exponential KEEAGOK.
That's really neat. So does this mean if Ag degrees for a reaction is negative, meaning spontaneous under standard conditions, its equilibrium constant K will be greater than 1, and if Ag is positive, K will be less than 1?
Precisely. Let's follow the math. If Ag degrees is negative, then the term 80 degrees in the exponent, Ag degrees, becomes positive. Since R and T are always positive, the whole exponent is positive. And Eg raised to any positive power is a number greater than 1. So if Ag degrees 0, then K1. This makes perfect sense. A reaction that is spontaneous under standard conditions will proceed forward to favor products at equilibrium. Conversely, if Ag degrees is positive, non-spontaneous under standard conditions, then the term Ag degrees becomes negative, making the whole exponent Ag degree negative. And E raised to a negative power is always a number less than 1. So if Ag degree is 0, then K1. This also makes sense. A reaction that doesn't want to proceed forward under standard conditions will have an equilibrium state that favors the reactants, resulting in very little product formation.
That's a beautiful and logical connection between spontaneity and the position of equilibrium. Let's try a quick calculation. In glycolysis, the phosphorylation of glucose has a standard Gibbs energy change, K degrees, of plus 13.8 kilojmol at 290 Kelvin. How do we find the equilibrium constant, Casey, for this reaction?
Okay, this is a great example connecting chemistry to biology, often relevant for NEET aspirants. First, we need to be careful with units. Ag degrees is given in kjmol, but the gas constant R, 8.314 jmol a jmol, uses joule. So convert Ag degrees to jmol, plus 13.8 kilonol, plus 13,800 jmol. Now we use our key formula. Ag degrees is RT ln Kc. We want to find Kc, so let's rearrange for ln Kc. ln Kc equals 13,800 jmol. Cum laude, 20 pounds and 98K. Calculate the denominator first. 8.314,298 is about 24777.6 jmol, 5.569. To find Kc itself, we need to take the exponent, the inverse of natural log. Kc equals E 5.569. Using a calculator, E caro is approximately 3.81 by 10^1 FLO.
Wow, that's a really small Kc value.
It is. And what does this small Kc tell us biologically? It means that under standard physiological conditions, this crucial first step of glycolysis, converting glucose to glucose 6-phosphate, is actually highly unfavorable thermodynamically. It doesn't spontaneously proceed to products. So how did our body make it happen? It cleverly couples this unfavorable reaction with a highly favorable reaction, usually the hydrolysis of ATP, adenosine triphosphate, which releases a lot of free energy, has a large negative K degrees. The overall coupled reaction then becomes favorable. This is a beautiful example of how biological systems utilize thermodynamic principles to drive essential processes. Understanding this link is very important.
That makes a lot of sense. It's not just about calculating K, but understanding what it implies.
Yeah.
Okay, let's shift now to something extremely practical, especially for industrial chemistry, the Chatelier's principle. How does it help us control reactions?
Le Chatelier's principle is arguably one of the most practical and frequently tested concepts when discussing equilibrium. It's the guiding principle behind maximizing product yield in countless industrial processes, none more famous than the Haber process for making ammonia, which, as you know, is essential for fertilizers and feeding the world. Formally, the principle states something like this. If a change of condition, a stress, is applied to a system in equilibrium, the system will shift in a direction that relieves the stress. Or more simply, a system at equilibrium, when disturbed, will adjust itself to counteract the effect of the disturbance. This principle applies to both physical and chemical equilibria. It helps us predict how an equilibrium system will respond to changes in concentration, pressure, or temperature. Remember, though, a crucial point. Only a change in temperature can alter the actual value of the equilibrium constant, KCEC or Kp. Other changes, like concentration or pressure, will shift the position of the equilibrium, meaning the relative amounts of reactants and products change, but won't change the Kt value itself for that temperature.
Okay, let's break it down. First, what happens if I change the concentration of one of the reactants or products in an equilibrium mixture?
Good question. If you change the concentration of a substance involved in the equilibrium, the system will react to minimize that change. If you add more of a reactant, the equilibrium will shift to the right towards products to consume some of that added reactant. If you add more of a product, the equilibrium will shift to the left towards reactants to consume some of that added product. If you remove a reactant, the equilibrium will shift to the left to replenish some of that removed reactant. If you remove a product, the equilibrium will shift to the right to replenish some of that removed product. Think of it in terms of the reaction quotient, Q. Adding a reactant decreases Q relative to K, so the reaction shifts forward. Adding a product increases Q relative to K, so it shifts backward. Removing a product decreases Q, shifting it forward. This is used extensively in industry. In Haber process, N euro plus 3 H euros to N H euro, the ammonia product is continuously liquefied and removed from the reaction chamber. Removing the product keeps the concentration of NH euros low, which, according to Le Chatelier, constantly shifts the equilibrium to the right, driving the reaction to produce more and more ammonia, and thus achieve a higher overall yield than would be possible if the ammonia were allowed to build up. Another example is the production of calcium oxide, quicklime, from heating limestone, KO-DOs plus CoA euro. This is done in open kilns where the KO euro gas produced is constantly removed. Removing the gaseous product drives the equilibrium continuously to the right, ensuring the decomposition goes to completion.
That makes sense. Constantly removing a product pulls the reaction forward. What about the effect of pressure change? How does that fit with Le Chatelier?
The effect of pressure change is primarily relevant for reactions involving gases, and importantly, only when the total number of moles of gaseous reactants is different from the total number of moles of gaseous products. Pressure changes are usually achieved by changing the volume of the container. Remember Boyle's law. P is inversely proportional to V at constant T. According to Le Chatelier's principle, if you increase the external pressure on a system at equilibrium, the system will shift in the direction that reduces the total number of gas molecules. Why? Because fewer gas molecules exert less pressure, thus counteracting the applied increase in pressure. Conversely, if you decrease the external pressure, for example, by increasing the volume, the equilibrium will shift in the direction that increases the total number of gas molecules, again counteracting the change. The volumes of pure solids and liquids are almost incompressible, so pressure changes have a negligible effect on equilibria involving only solids and liquids, or where the number of gas moles doesn't change.
So for the Haber process again, Ng plus 3Ag, it goes from 4 moles of gas on the left to 2 moles of gas on the right. So increasing the pressure would favor making more ammonia.
Exactly. High pressure favors the side with fewer moles of gas. In the Haber process, reactants, N-udo plus 3 euros, constitute 4 moles of gas, while the product, 2NH, is only 2 moles of gas. Therefore, applying high pressure, typically around 150-250 atmospheres or even higher in some plants, shifts the equilibrium significantly to the right, favoring ammonia formation and increasing the yield. This is a key factor in the industrial process design. Conversely, consider a reaction like the decomposition of calcium carbonate, CaNO plus TOJ. Here you go from 0 moles of gas on the left, ignoring the solid, to 1 mole of gas on the right. Increasing the pressure would actually shift this equilibrium to the left, favoring the reformation of solid CaCO, as that reduces the amount of gas.
Okay, that's clear. Now, a tricky one I often see in MCQs. What happens if you add an inert gas, like argon or helium, to an equilibrium mixture? Does that shift things?
Yes, the inert gas addition, a classic question designed to test your understanding. The effect depends on how the inert gas is added. If an inert gas is added at constant volume, adding an inert gas increases the total pressure inside the container. However, it does not change the partial pressures or the molar concentrations of the reacting gases. Since the partial pressures or concentrations that go into the K or Kc expression remain unchanged, the reaction quotient Q does not change. Therefore, adding an inert gas at constant volume has no effect on the position of the equilibrium. If an inert gas is added at constant total pressure, this scenario implies that as the inert gas is added, the volume of the container must increase to keep the total pressure constant. Increasing the volume does affect the equilibrium if the known is not zero. An increase in volume lowers the partial pressures of all reactant gases. The system will then shift towards the side with more moles of gas to counteract this effective dilution or decrease in partial pressures. For most exam purposes, unless stated otherwise, adding an inert gas usually implies addition at constant volume, meaning no effect on the equilibrium position. But be sure to read the question carefully.
That's a very crucial distinction. Constant volume versus constant pressure. Thanks. Finally, how does temperature change affect equilibrium according to Le Chatelier? You mentioned earlier it's the only thing that changes K itself?
Yes, temperature is unique. It affects both the position of equilibrium and the value of the equilibrium constant, K. Le Chatelier's principle still applies beautifully. The system will shift in a direction that counteracts the temperature change. Think of heat as being like a reactant or a product. For an exothermic reaction, A is negative, meaning heat is released, so you can think of heat as a product. Reaction plus heat. If you increase the temperature, add heat, you are adding a product. The equilibrium will shift to the left, towards reactants, to consume this added heat. The shift to the left means the value of K, ratio of products to reactants, will decrease. If you decrease the temperature or remove heat, you are removing a product. The equilibrium will shift to the right, towards products, to generate more heat. This shift to the right means the value of K will increase. For an endothermic reaction, ADH is positive, meaning heat is absorbed, so you can think of heat as a reactant. Heat plus reaction equals products. If you increase the temperature, add heat, you are adding a reactant. The equilibrium will shift to the right towards products to consume this added heat. This shift to the right means the value of K will increase. If you decrease the temperature, remove heat, you are removing a reactant. The equilibrium will shift to the left towards reactants. This shift to the left means the value of K will decrease. Let's revisit the Haber process. N euro plus 3 Hers equals 2 NH. It's exothermic. NH 92 kilomole. So according to Le Chatelier, lower temperatures favor higher equilibrium yields of ammonia, larger K. However, there's a practical problem. At low temperatures, the reaction rate becomes extremely slow. This is a classic trade-off in chemical engineering. Equilibrium versus kinetics. High temperatures give fast rates, but poor equilibrium yields. Low temperatures give good yields, but impractically slow rates. The solution involves using a moderate temperature, around 400 and 500 degrees C, combined with high pressure and a catalyst. A great visual demonstration is the equilibrium between nitrogen dioxide, NO, brown gas, and dinitrogen tetroxide, NO, colorless gas, a 2NO euro. This reaction is exothermic. NEH is negative 57.2 kilomole. If you take sealed tubes containing this mixture and place one in ice water, low T, the brown color fades significantly as the equilibrium shifts right towards colorless NOO. If you place another tube in hot water, high T, the brown color intensifies dramatically as the equilibrium shifts left towards brown NOO. This clearly shows the temperature effect predicted by Le Chatelier.
That trade-off between yield and rate for the Haber process makes the role of catalysts very clear. So let's talk about catalysts. How exactly do they fit into the equilibrium picture? Do they shift the equilibrium according to Le Chatelier?
That's another critical point for exams, and a common source of confusion. Catalysts are substances that increase the rate of a chemical reaction without being consumed in the overall process. They do this by providing an alternative reaction pathway with a lower activation energy. However, here's the crucial part regarding equilibrium. A catalyst speeds up both the forward reaction and the reverse reaction by the exact same factor. It lowers the energy barrier for both directions equally. Because it speeds up both rates equally, a catalyst does not affect the position of equilibrium. It does not change the equilibrium concentrations of reactants or products, and it does not change the value of the equilibrium constant K. What a catalyst does do is help the system reach equilibrium faster. So in the Haber process, the iron-based catalyst doesn't give you a higher percentage yield of ammonia at equilibrium for a given temperature and pressure, but it allows that equilibrium yield to be reached much, much more quickly, making the process economically viable at the moderate temperatures where the equilibrium yield is still reasonably good. Without the catalyst, the reaction at those temperatures would be far too slow. Another example is the contact process for making sulfuric acid involving the step 2SO plus O 2SOG. This reaction is highly favorable thermodynamically, large K, but very slow kinetically. Catalysts like vanadium pentoxide VROs are essential to achieve a satisfactory rate. Just remember, if a reaction has an extremely small K value, meaning equilibrium lies far to the left with almost no product, a catalyst won't magically make more product appear. It will just help you reach that unfavorable equilibrium state more quickly. Catalysts affect rates, not the ultimate equilibrium position.
That's a very clear distinction. Catalysts for speed, the Chatelier TP concentration for position. Okay, this provides a solid foundation for chemical equilibrium. Now let's dive into the second major part, ionic equilibrium in solution. This seems crucial for understanding acids, bases, pH, buffers, basically a huge chunk of chemistry, especially relevant for biology too.
Indeed. Ionic equilibrium deals with the equilibrium involving ions in solution, primarily in water. It's fundamental to understanding acid-base chemistry, solubility, and many biological and environmental processes. We begin with the concept of electrolytes. You've probably observed in the lab that some aqueous solutions, like salt water, NaCl, and water or acid solutions conduct electricity, while others, like sugar dissolved in water, do not. Substances whose aqueous solutions conduct electricity are called electrolytes. Those that don't are non-electrolytes. The reason electrolytes conduct electricity is because they produce mobile ions, positively charged cations, and negatively charged anions when dissolved in water. These mobile charges carry the electric current.
And electrolytes aren't all the same, right? I remember terms like strong and weak electrolytes.
Exactly. We classify electrolytes based on the extent to which they produce ions in solution. Strong electrolytes. These substances are assumed to be almost completely, 100% ionized or dissociated when dissolved in water. Examples include soluble ionic salts like NaCl, strong acids like HCl, HARO, HNOs, and strong bases like NaOH, KOH. When you dissolve NaCl in water, you essentially get NiO and ClO ions with virtually no undissociated NaCl units remaining. Weak electrolytes. These substances only partially dissociate or ionize in water. At equilibrium, the solution contains a mixture of the undissociated molecules and a relatively small concentration of ions. Acetic acid, the CH2OH, the acid in vinegar, is a classic example. In a typical solution, maybe less than 5% of the acetic acid molecules actually ionize into HO and CH ions. Most remain as intact HO molecules. Other examples include weak bases like ammonia, NHO. Ionic equilibrium, then, is specifically the study of the dynamic equilibrium established between the ions and the unionized molecules in solutions of weak electrolytes.
Okay, that makes sense. So this leads us to acids, bases, and salts. We have everyday ideas about them. Acids are sour, bases are bitter, salts foam when they react. But how do chemists define them more precisely, especially for understanding ionic equilibrium?
Good question. Our everyday notions are useful starting points, but chemists have developed more rigorous definitions over time to explain a wider range of chemical behavior. There are three main concepts of acids and bases you need to be familiar with for your exams. First, the earliest formal definition is the Arrhenius concept. Sponte Arrhenius proposed this around 1884. An Arrhenius acid is a substance that produces hydrogen ions, He, when dissolved in water. For example, a generic acid HX dissociates. HETQ plus XU2. We should note that the bare proton HU is extremely reactive and doesn't really exist freely in water. It immediately attaches to a water molecule to form the hydronium ion HEETD. So chemists often use He and HE interchangeably to represent the acidic species in water. An Arrhenius base is a substance that produces hydroxide ions, OHHU, when dissolved in water. For example, sodium hydroxide, NaOH, dissolves and dissociates. NeOH plus OHE2. The main limitation of the Arrhenius concept is that it's restricted to aqueous solutions only. It also couldn't explain why some substances, like ammonia, NHROs, exhibit basic properties even though they don't contain an OH group in their formula.
Right, ammonia is basic, but doesn't fit the MOH formula. So that's where the next definition comes in, the Brønsted-Lowry concept.
Precisely. Around 1923, Johannes Brønsted and Thomas Lowry independently proposed a more general definition that overcomes the limitations of the Arrhenius theory. The Brønsted-Lowry concept defines acids and bases based on proton transfer. A Brønsted-Lowry acid is a proton donor, an Ig donor. A Brønsted-Lowry base is a proton acceptor, an A acceptor. This definition is much broader, it's not restricted to aqueous solutions, and it explains the basicity of substances like ammonia. Let's look at ammonia reacting with water, NHRQ plus HRO plus OAAQ. In the forward reaction, the water molecule, HRO, donates a proton to the ammonia molecule, Na. Therefore, HRO acts as the Brønsted-Lowry acid, and NH acts as the Brønsted-Lowry base. Now look at the reverse reaction. The ammonium ion, NHRO, donates a proton back to the hydroxide ion, OH, so in the reverse direction, NHRO is the acid and OO is the base.
And this leads directly to the idea of conjugate acid-base pairs, right, where they differ just by one proton.
Exactly. A conjugate acid-base pair consists of two species that are related by the gain or loss of a single proton. When a Brønsted-Lowry acid donates a proton, the species remaining is called its conjugate base. In our example, OO is the conjugate base of the acid HO. When a Brønsted-Lowry base accepts a proton, the species formed is called its conjugate acid. In our example, NH is the conjugate acid of the base NH, so we have two conjugate pairs in this reaction, HEOO and HEO and HO. A crucial relationship, often tested, is the inverse strength relationship. The stronger the acid, the weaker its conjugate base, and vice versa. For example, HCl is a very strong acid, meaning it gives up its proton very easily. Its conjugate base, the chloride ion, ClO, is consequently a very weak base. It has almost no tendency to accept a proton back. Conversely, acetic acid is a weak acid. Its conjugate base, the acetate ion, is a relatively stronger base than Cl. Also, notice in the ammonia example, water acted as an acid. But if water reacts with a strong acid like HCl, HClHu plus HRO plus ClOQ. Here, HCl donates the proton, so HCl is the acid, and water accepts the proton, making water the base. Substances like water that can act as either an acid or a base are called amphiprotic or amphoteric.
That concept of conjugate pairs and amphiprotic nature makes a lot of sense. So what about the third definition, the Lewis acids and bases? How is that different?
The Lewis concept, proposed by G.N. Lewis, also around 1923, provides the most general definition of acids and bases, focusing on electron pairs rather than protons. A Lewis acid is defined as an electron pair acceptor. A Lewis base is defined as an electron pair donor. This definition encompasses all Brønsted-Lowry acids and bases, but it's even broader. Think about the Brønsted-Lowry base. It accepts a proton. To accept a proton, Mu, which has no electrons, the base must have a lone pair of electrons available to form a coordinate covalent bond. So all Brønsted-Lowry bases are also Lewis bases, electron pair donors. The Lewis definition, however, includes acids that don't necessarily involve protons. A classic example is boron trifluoride, Be. Boron in BF only has 6 electrons in its valence shell, so it has an empty orbital and can accept a pair of electrons. Ammonia has a lone pair on the nitrogen atom. When they react, ammonia donates its lone pair to boron, forming a coordinate bond. BF plus Dan and HEs. In this reaction, BFEs acts as the Lewis acid electron pair acceptor, and NAs acts as the Lewis base electron pair donor. Other examples of Lewis acids include electron-deficient molecules like alkors, metal cations like ferro or cor, which can accept electron pairs from ligands, and even the proton HU itself. Lewis bases are simply species with available lone pairs like H0 and H0OS.
Okay, so Lewis is the broadest definition, focusing on electron pairs. That clarifies the different ways chemists classify these fundamental species. Now, let's connect this back to ionic equilibrium and talk about the ionization constants that measure the strength of weak acids and bases.
Right. We know strong acids and bases dissociate almost completely in water, but for weak acids and weak bases, the extent of dissociation is limited, and we quantify this using equilibrium constants. For a generic weak acid, HA, ionizing in water, HAQ plus HOL plus AOLAQ, the equilibrium constant for this ionization is called the acid ionization constant, denoted as kapha. Its expression is kapha HOAOAO. Remember, we omit the concentration of water as it's the solvent and effectively constant. The value of Ka tells us the strength of the weak acid. A larger Ka value means a stronger acid, more dissociation, higher HO at equilibrium. We often use pK neslagogo as well. Since it's a negative log, a smaller pK value indicates the stronger acid. You'll often find tables of Ka or pK values for various weak acids in your textbooks, like Table 6.6 and NCERT. We can also relate Ka to the degree of ionization HO alpha, which is the fraction of the acid molecules that have ionized. If the initial concentration of the acid is C, then at equilibrium, HOOCO AHA and HAOC1. Substituting these into the Ka expression gives a very useful formula, often called Ostwald's dilution law for weak acids. Ka equals 110. If the acid is very weak, Icali is very small compared to 1, we can often approximate 101, simplifying this to Ka Aka.
That formula relating Ka, concentration C, and alpha seems really important for calculations.
It is extremely important. You'll use it frequently to calculate pH, percentage ionization, or Ka itself in numerical problems.
Okay, before we jump into calculations, what about the ionization constant of water itself? You mentioned water self-ionizes slightly.
Yes, the autoionization of water is fundamental to understanding pH. Water, being amphiprotic, can react with itself. One molecule acts as an acid, another as a base, HOL plus OA. The equilibrium constant for this process is called the ionic product of water, denoted as QOO. Since the concentration of pure water is essentially constant, it's incorporated into the constant, leaving. The value of QPOA is temperature dependent. At standard room temperature, 298 Kelvin, 25 degrees, QOGO has a value of 1.0.10 OOM. This is a crucial value to memorize. In pure neutral water at 298 K, the concentrations of Ig and OL must be equal due to the 1.1 stoichiometry of autoionization. So HOO 0.0 to 10 never equals 1.0.0 OAOPOM. This tiny concentration is why pure water is a very poor conductor of electricity.
And this directly leads to the pH scale, right? Because working with numbers like 10 is cumbersome.
Exactly. The pH scale was introduced by Sørensen in 1909 to provide a more convenient way to express the very small concentrations of H ions. pH is defined as the negative logarithm, today's 10, of the hydrogen ion concentration, or more accurately activity, but concentration is usually used for dilute solutions. pH equals log H, using this definition. For a neutral solution at 298 K, where H equals 1.0 of 10 RLM, pH equals log 10 equals 7. For an acidic solution, H equals 1.0 of 10 L 10 RL, which means the pH will be less than 7. For example, if H rho A of pH equals 3. For a basic or alkaline solution, H 1.0 H 10 R, which means the pH will be greater than 7. For example, if H equals 10 OM, pH equals 9. We can also define POH log OH. And since KWOH, if you take the negative logarithm of the whole KW expression, we get Nesh log KW plus Next log OH. This gives us another vital relationship, PKW equals pH plus POH. Since KWH 10 arrow at 298K, PKW equals 14. So at 298K, pH plus POH equals 14. This allows you to easily convert between pH and POH. Remember the logarithmic nature. A change of 1 pH unit corresponds to a 10-fold change in nature concentration. A solution of pH 3 is 10 times more acidic than pH 4 and 100 times more acidic than pH 5.
That pH plus POH equals 14 relationship is super useful. Okay, let's revisit the tricky problem. Calculating the pH of a very dilute strong acid, say 1.0 pi and 10 alky MHCl. How do we use KW here?
Right. This is where we absolutely cannot ignore the H contribution from water's autoionization, because the H from the acid itself, 10 OM, is even less than the H normally present in pure water, 10 OM. Here's a systematic approach. 1. Identify all sources of H. We get H from the complete dissociation of HCl, which gives H sub HCl sub equals 1.0 or 10 OM. We also get H from the autoionization of water. HU equals H plus OO. Let the concentration of H and OO coming from water be X. 2. Write the expression for the total hydrogen ion concentration. A sub total sub H sub HCl sub plus H sub water sub 1.0 X is 10O plus XM. 3. The concentration of hydroxide ions comes only from water in this case. OS sub total sub equals 1.0 OS X come. 4. Now apply the ionic product of water equilibrium. KW her subtotal sub 0 subtotal sub 1.0 O 10 O. Substitute our expressions. 1.0 and 10 O plus X 1.0 10 O. 5. Solve this equation for X. It's a quadratic equation. X plus 1.0 at 10 OO by 1.0 of 10 OINO. Using the quadratic formula, you'll find the positive root for X is approximately 9.510 OM. This value, X, represents OSH. 6. Now find the total height. How subtotal sub equals 1.0 plus x, I plus 1.0 plus 9.5 current 10 euros, by 10 euros, 1.05 die 10 euro by 10 7. Finally, calculate the pH is not and 10 log 1.05 times 10. This comes out to be approximately 6.98. Notice the result. The pH is slightly less than 7, which makes sense because we added a small amount of acid. It didn't become basic, pH 8, as the naive calculation suggested. This problem is a favorite for testing a deep understanding of ionic equilibrium.
That detailed breakdown makes it much clearer why we need to consider water's contribution in such cases. Okay, now let's properly tackle calculations for weak acids. How do we typically find the pH or degree of ionization using COCA?
Right, for weak acids, we generally need to use the Ca value and the initial concentration, often employing the ICE table method again. Let's work through a standard example. Suppose we need to calculate the degree of dissociation, the concentration of all species at equilibrium, and the pH for a 0.02 m solution of hydrofluoric acid. We're given that Ca for HF is 3.2 over 10 over. Step 1. Write the ionization equilibrium. HFAQ plus HOOL plus SOOR. Step 2. Set up the ICE table. I, initial M, H of 0.02, HOR, neglecting waters 10 euro, F00. C, change M. Let X be the concentration of HF that ionizes. Change is near X for HF plus X for HO plus X for XE equilibrium M. HF 0.02 max HOXX. Step 3. Substitute into the CAT expression CAT HOXX 0.02X. So 3.2 half tram X, 3.2.x CO. Step 4. X 0.2 X layer 2 X inclined at 6.4 times 10 to the 0.2 by 2x, rearranging x plus 3.2 at pi 6.4 at 10 to 0 there. Using the quadratic formula, but the x par 4 AC 2a, where a1 b 3.2 at 10 euro, c pass 6.4 time can 10 euro. Solving this gives a positive root for x os 2.38, 10 x. The negative root is discarded. Step 5. Calculate equilibrium concentrations in x 7.4 to x 7 toro, rounding slightly. X at 0.4 10 x x to x equals 0.0.0024 x 0.0 was over to 0.002. Degree of dissociation x huge amount ionized initials about x 0.4 and 0.2 random super large noise 0.3 about 12% of ionization. Step 6. Calculate pH often quadratic knock-on concentrations and extra fixed. pH is standard procedure for weak acid problems. Sometimes if case cross is very small compared to C, they might be simplified the calculation and finding concentrations and pH is the standard procedure for weak acid problem. Sometimes, if SOCA is very small compared to C, you might be able to simplify the calculation by approximating CXXC, avoiding the quadratic formula, but it's safer to check if that assumption is valid.
That's a thorough walkthrough. What if the problem is reversed? Like if we know the pH of a weak acid solution and its initial concentration, can we find its Ka?
Absolutely. That's another common problem type. Let's say you prepare a 0.1 m solution of a certain monobasic acid, meaning it has one acidic proton, HAJA, and you measure its pH to be 4.50. Can we find Ka and Palumbi Ka? Step 1. Find Ha from pH, Ha 10 OGA, using a calculator, 10 OGL, 3.16 AO10. Step 2. Consider the equilibrium, HA or sen A plus A. From the stoichiometry, the concentration of the conjugate base A formed must be equal to the concentration of A2 formed by ionization. So AO3.16 at 10 OM. Step 3. Find the equilibrium concentration of the undissociated acid, HA. Because initial sub has a form sub 8.1 m 3.16 at 10 m. Since the amount ionized 3.16 at 10 is very small compared to the initial concentration 3.1, we can often approximate Hasselbeck sub initial sub a, which is 0.1. Step 4. Calculate Ka using the equilibrium concentrations. Ka is 3.16 then 3.1 length layer at 0.11.0 10 1 cents. So that's step 5. Calculate Pk is 1.0 10 and 8.0. So by measuring the pH of a solution with a known initial concentration, we can determine the ionization constant of the weak acid. This is a fundamental way Cal values are experimentally determined.
That's great. Now, how does all this apply to weak bases? Is the process similar, just using Kb instead of K?
Very much so. The principles are identical, but we focus on the production of hydroxide ions and use the base ionization constant, Kb. For a generic weak base, B reacting with water, which acts as the acid here, BAQ plus HOL plus OAQ. BHA is the conjugate acid of the base B. The base ionization constant Kb is defined as Kb equals BHOOB. A larger Kb value means a stronger weak base. Similarly, pKb equals log euro, and a smaller pKb indicates a stronger base. Table 6.7 in your textbook lists Kb values for common weak bases like ammonia and various amines. The relationship with the degree of ionization and initial concentration, C, is also analogous. Kb simplifies to Kb is small. To find the pH of a weak base solution, you typically first calculate OH using Kb and the ICE method, then find POH logo, and finally use pH log 14 POH at 298 K.
Okay, let's try an example. Calculate the pH of a 0.05 M ammonia solution. We know Kb for NH is a 1.77 P10 form.
All right, the reaction is NHOs plus HO plus OO. We can use the approximate formula Kb XOs to find A first, or directly calculate OA. Let's assume OA is X. Then NHO is X and NHO at 0.05. NHO is X0 is 0.05. X and X 0.05. X 0.05. So 1.77 X 0.05. Solve for X or 0.77 times 0.05 equals 8.85. If X for X, 8.85 to SO is 7, 9.4 at 10 a row. This value X represents the equilibrium concentration of OO, note, is by 0.05. Yes, 9.4 times 10 or is much smaller than 0.05, so our approximation was valid. And now calculate POH. POH in this log, 9.4 to 10 RO is 3.03. Finally, calculate pH. POH is 14. 3.03 equals 10.97. So the 0.05 N ammonia solution is basic with a pH of nearly 11.
That makes sense. And you mentioned earlier there's a really important relationship between the Ka of an acid and the Kb of its conjugate base.
Absolutely. This relationship is incredibly useful and simplifies many calculations. For any conjugate acid-base pair, the product of the acid ionization constant of the acid and the base ionization constant of its conjugate base is equal to the ionic product of water, KW, KAB, KW. Let's prove this quickly using the ammonium-ammonium pair. The acid dissociation of the conjugate acid NHU is NHU plus AHU plus NHU. The constant for this is Kb. The base ionization of the base, NHU, is NAU plus HOL plus OL. The constant for this is Kb NHU. Now multiply Chi by Kb, KAA, NHO, NH. Notice that NHO and NHU cancel out, leaving KAAA, and we know that HO is simply KW, so K for NH or NHW. This holds true for any conjugate acid-base pair in water. This relationship mathematically confirms the inverse strength principle. If K is large, strong acid, Kb must be small, very weak conjugate base, and vice versa, because their product must equal the very small constant Kw, 10 at 298 K. In terms of pK values, taking the negative logarithm of the equation Kx Tb equals Kw gives Kk plus Pkb equals Pkw. Since Pkw was 14 at 298 K, we have the extremely useful relation Pka plus Pkb equals 14 at 298 K. If you know the pK of an acid, you immediately know the Pkb of its conjugate base, and vice versa.
That formula, pKt plus Pkb equals 14, is definitely one to remember. It seems like a great shortcut.
It is indeed.
What about acids that can donate more than one proton, like sulfuric acid or phosphoric acid?
Yeah.
How do we handle their ionization?
Good question. Those are called dioro and polybasic acids, or triprotic acids. They ionize in steps, and each step has its own ionization constant. Let's take a generic diprotic acid, HRO. First ionization, HOQ plus HOOL plus HOOQ plus HOO. This step has an acid ionization constant K1. Second ionization, HOO plus HOO, OAQ plus HOA. This step has its own constant K2. There's a general trend you must know, K1, KO2, K10, for polyprotic acids. It's always easier to remove the first proton from the neutral molecule HOA than it is to remove the second proton from an already negatively charged ion. The negative charge on HAO makes it harder to pull away another positive proton due to electrostatic attraction. For many practical calculations involving polyprotic acids, especially weak ones, the HO concentration in the solution is primarily determined by the first ionization step, KO1, because KO2 and subsequent K are usually much smaller. So you often only need to consider the first step to get a good estimate of the pH, unless specifically asked otherwise. Similar principles apply to polyacidic bases that can accept more than one proton.
Okay, that makes sense. The first proton comes off easiest. Now, we talked a lot about measuring acid strength with Kappa. What actually makes an acid strong or weak at a molecular level? What factors affect acid strength?
That's delving into the relationship between molecular structure and acidity, which is very important. There are two main factors that determine the strength of a binary acid, HA. 1. The strength of the HA bond. How much energy is required to break the bond between hydrogen and the other atom? A weaker HA bond, less energy needed to break it, means the proton can leave more easily, resulting in a stronger acid. This factor is generally dominant when comparing acids within the same group in the periodic table. For example, moving down the halogen group, the HX bond strength decreases. HF, HCl, HBr, HI. Consequently, acid strength increases down the group. HF is a weak acid, while HCl, HBr, and HI are all strong acids. Similarly, HS is a stronger acid than HO because the HS bond is weaker than the HO bond. 2. The polarity of the HA bond. How unevenly are the electrons shared in the bond? A more polar HA bond, due to a larger difference in electronegativity between H and A, means the hydrogen atom carries a greater partial positive charge, making it easier for it to leave as HO. This results in a stronger acid. This factor is generally dominant when comparing acids across the same period in the periodic table. For example, moving across the second period from carbon to fluorine. CH arrow, NH arrow, HF. Electronegativity increases significantly, CNOF, making the HA bond more polar. Thus, acid strength increases across the period. Methane is essentially non-acidic, ammonia is very weakly acidic, acting as a base is more common, water is weakly acidic, and HF is a weak, but the strongest in that series, acid. So you need to consider both bond strength and polarity, and which factor dominates depends on whether you're moving down a group or across a period.
That structural explanation is really helpful. Now let's bring back the common ion effect. We saw how it affects weak acid ionization. Does it play a role elsewhere too?
Absolutely. The common ion effect is a fundamental principle that influences several types of ionic equilibria, most notably the ionization of weak acids and bases, as we discussed, and also the solubility of sparingly soluble salts, which we'll get to shortly. It's essentially Le Chatelier's principle applied to solutions containing a common ion. Remember the definition. The common ion effect is the shift in an ionic equilibrium caused by the addition of a solute that provides an ion that is already part of the equilibrium. For weak acids, like acetic acid, HOP plus sapor, adding a source of acetate ions, the common ion, such as sodium acetate, NaCsO, shifts the equilibrium to the left. This suppresses the ionization of acetic acid, decreasing the opacity and increasing the pH. Similarly, for a weak base, like ammonia, NH plus Aro plus OHO, adding a source of ammonium ions, the common ions, such as ammonium chloride and HAOR, shifts the equilibrium to the left. This suppresses the ionization of ammonia, decreasing the OR and lowering the pH, making it less basic. This effect is the basis for how buffer solutions work, as we'll see.
Okay, so the common ion effect suppresses the ionization of weak electrolytes. This naturally leads us to discuss hydrolysis of salts. What happens when we dissolve salts in water? Does the pH always stay neutral?
Not necessarily. That's a common misconception. While dissolving a salt like NaCl, formed from a strong acid, HCl, and a strong base, NaOH, in water results in a neutral solution, pH equals 7, this isn't true for all salts. Salt hydrolysis refers to the reaction of the anions or cations, or both, of a salt with water, which can change the concentration of HO or O ions, thus affecting the solution's pH. We need to consider the nature of the acid and base from which the salt was formed. 1. Salts of strong acid and strong base, e.g., NaCl, KBr, NONO. Neither the H-HU cation, like NaU, CaO, which are conjugate acids of strong bases, nor the anion, like Clay and Bro, NoU, which are conjugate bases of strong acids, has any significant tendency to react with water. They are merely hydrated, therefore these solutions are neutral, pH equals 7 at 298 K. 2. Salts of weak acid and strong base, for example, Cheshuna, NeCN, KF. The salt fully dissociates Cirrus, Shushia, or A plus Cheshio. The cantio doesn't react with water. However, the anion, the acetate ion, is the conjugate base of a weak acid, acetic acid. It's a relatively strong base and will react with water, hydrolysis. TSCO plus IO plus HO plus OO. This reaction produces hydroxide ions, making the solution alkaline basic, so pH 7. 3. Salts of strong acid and weak base, e.g. NH EOHC, NHO plus O. The salt fully dissociates Ag NHUl plus the NHUl doesn't react with water. However, the cation, NHUl of the ammonium ion, is the conjugate acid of a weak base, ammonia. It's a relatively strong acid and will react with water, hydrolyze. NHU plus HUS plus HUL plus NHUO plus HCl. This reaction produces hydronium ion, HU or H, making the solution acidic, so pH 7. 4. Salts of weak acid and weak base, e.g. HUO, NHEO. This is the most complex case. Both the cation, e.g. NHU, and the anion, U2O, hydrolyze. The cation produces H and the anion produces OOO. The overall pH of the solution depends on the relative strength of the weak acid and the weak base from which the salt was formed, specifically on their K and Kb values, or pKa and pKkb. The pH can be calculated using the formula pH P7 plus pKa Kb at 298 K. If pKa equals pKb, acid and base are equally weak, the solution is neutral, pHa 7. Example, ammonium acetate, pKa 4.76, pKb NH 4.75. If pKa, pKb, acid and base are equally weak, the solution is neutral, pHa 7. Example, if pKb, acid is stronger than the base is weak, the solution is acidic, pH 7. If pKb, acid and base are equally weak, the solution is neutral, pHa 7. Example, if pKb, base is stronger than the acid is weak, the solution is basic, pH 7.
That formula for salts of weak acids and weak bases is interesting. So for ammonium acetate, since pKa and pKb are almost identical, the pH should be very close to 7.
Exactly. Let's plug in the values for ammonium acetate. pKa of acetic acid is 4.76 and pKb of ammonia is 4.75. pH score 7 plus karate, a pleo 7 plus half talent equals 7.01 equals 7 plus 0.005 plus 7.005. So the solution is almost perfectly neutral, maybe just ever so slightly basic because the base ammonia is just marginally stronger, slightly smaller pKb than the acetic acid is weak.
Understanding salt hydrolysis is clearly key to predicting pH. Now, this seems like the perfect lead-in to buffer solutions, which resist pH changes. How do they work, based on what we've learned?
You're right. The concepts of weak acids bases and the common ion effect are the foundation for understanding buffers. Buffer solutions, as you said, are remarkable solutions that resist large changes in their pH, even when small amounts of strong acid or strong base are added or upon dilution. This buffering capacity is absolutely vital in biological systems. Our blood, for instance, is buffered primarily by the carbonic acid bicarbonate system, H2O Europe, to maintain a very stable pH around 7.4. Buffers are also crucial in many chemical processes, analytical chemistry, and in formulating medicines and cosmetics.
So what are the typical components of a buffer? How are they made?
There are two main types of buffer solutions you need to know. 1. Acidic buffer. This is a solution containing a mixture of a weak acid and its salt with a strong base. The salt provides the conjugate base of the weak acid. The classic example is a mixture of acetic acid, sodium acetate, and sodium acetate, COCona, the salt providing the conjugate base, COCona. This buffer system is most effective at maintaining pH values around the pKa of acetic acid, which is about 4.75. 2. Basic buffer. This is a solution containing a mixture of a weak base and its salt with a strong acid. The salt provides the conjugate acid of the weak base. The standard example is a mixture of ammonia, NHOs, often written as NHOH in water, the weak base, and ammonium chloride, NHOHO, the salt providing the conjugate acid NHRO. This buffer system is most effective around the pKa of the conjugate acid NHRO, which is about 9.25. Since pKb of NHRO is 4.75, pKa is 14, 4.75 yields 9.25. The key is having significant concentrations of both the weak acid base and its conjugate partner present in the solution.
And how does this mixture resist pH changes? What happens when you add acid or base?
Let's take the acidic buffer, HAAO, example, acetic acid acetate, as an example. If you add a small amount of strong acid, the added AHO ions will react with the conjugate base component of the buffer AO plus A, HA. This converts the strong acid H into the weak acid HA, so the pH change is minimal. If you add a small amount of strong base, OY, the added OIO ions will react with the weak acid component of the buffer, OO plus HAAO plus A. This converts the strong base OIO into water and the weak conjugate base A, again minimizing the pH change. The buffer works because it has components that can effectively neutralize small amounts of added acid or base. The same logic applies to basic buffers, BHO.
That's clever. And how do we calculate the specific pH of a buffer solution, or design a buffer for a target pH? I think you mentioned the Henderson-Hasselbalch equation earlier.
Yes. The Henderson-Hasselbalch equation is the essential tool for buffer calculations and design. It's derived directly from the K expression for a weak acid. For an acidic buffer, weak acid HA and its conjugate base AO, usually from a salt. The K expression is KHAO, rearranging for HIC, AOO equals AHA, taking the negative logarithm of both sides. Next, log O, this log HAO. This becomes PHHABO plus log OHA. Since the conjugate base A primarily comes from the dissolved salt and HA is the undissociated weak acid, this is commonly written as. PHHA is the undissociated weak acid, this is commonly written as. PHPKA plus log O or salt acid. This is the Henderson-Hasselbalch equation for acidic buffers. It allows you to calculate the pH of a buffer if you know the pK of the weak acid and the concentrations of the acid and its salt. Notice a key point. If the concentration of the salt equals the concentration of the acid, then salt to acid equals 1 and log 1 equals 0. In this case, pH equals PA. This means a buffer is most effective, has maximum buffering capacity, when the pH is equal to the pK of the weak acid, which occurs when the concentrations of the acid and its conjugate base are equal. To prepare a buffer of a desired pH, you should choose a weak acid whose pK is close to that target pH, and then adjust the ratio of salt to acid to fine-tune the pH using the equation. For basic buffers, weak base B and its conjugate acid BHO from a salt, you can derive a similar equation for POH. POH is pKb plus log euros, conjugate acid base, where conjugate acid usually comes from the salt concentration. You can then find the pH using pH 14 POH. Alternatively, you can express it directly in terms of pH by using the pKa pKa of the conjugate acid, remember pKa plus pKb equals 14, pH pK of conjugate acid plus log euro base conjugate acid. For the ammonium chloride buffer, the conjugate acid is NH at pKa is 9.25, so pH weaks 9.25 plus log US. One practical advantage of buffers is that their pH is relatively insensitive to dilution because dilution affects the concentrations of both the acid base and its conjugate pair equally, leaving their ratio largely unchanged in the Henderson-Hasselbalch equation.
That equation is definitely key for buffer problems. Okay, we've covered a lot on acids, bases, and buffers. Let's move to the final major topic in ionic equilibrium: solubility equilibria of sparingly soluble salts. Why do some salts like AgCl barely dissolve, while others like NaCl dissolve so readily?
That's right, there's a huge variation in the solubility of ionic solids in water. Understanding why involves considering the energetics of the dissolution process, which depends on a balance between two main factors. One, lattice enthalpy, or lattice energy. This is the energy required to break apart 1 mole of the solid ionic crystal lattice into its constituent gaseous ions. Breaking these strong electrostatic attractions always requires energy input, so lattice enthalpy is positive. 2. Solvation enthalpy, often hydration enthalpy if the solvent is water. This is the energy released when 1 mole of gaseous ions becomes surrounded and stabilized by solvent molecules. This interaction between ions and solvent dipoles is favorable, so solvation enthalpy is always negative, exothermic. The overall enthalpy change of dissolution is roughly the sum of these two, lattice enthalpy plus solvation enthalpy. For a salt to dissolve readily, the energy released during solvation must be large enough to overcome the energy required to break the lattice. Essentially, for significant dissolution, the magnitude of the negative solvation enthalpy should be greater than the positive lattice enthalpy. Solubility is a characteristic property for each salt at a given temperature. We often classify salts based on their solubility in water at room temperature. Soluble. Solubility greater than about 0.1 mm, slightly soluble. Solubility between 0.01 and 0.1 mm, sparingly soluble or insoluble. Solubility less than 0.01 mm. It's important to remember that even insoluble salts dissolve to a tiny extent. Our focus in this section is on the equilibrium involving these sparingly soluble salts.
And for these sparingly soluble salts, we use the solubility product constant, KSP, to describe their equilibrium, right?
Precisely. When a sparingly soluble ionic salt is placed in water, it dissolves to a small extent, establishing an equilibrium between the undissolved solid and its ions in the saturated solution. Consider a generic sparingly soluble salt like barium sulfate, base SO. Base O, base O, base O plus SOUO. We can write an equilibrium constant expression for this. K equals base O, base OO. As we learned with heterogeneous equilibria, the concentration or activity of the pure solid base O is constant. So we incorporated into the equilibrium constant to define a new constant called the solubility product constant, KSP. KSP equals base OO. KSP represents the product of the ion concentrations raised to their stoichiometric powers in a saturated solution at a given temperature. For base SO at 298 K, KSP is about 1.1 A's 10 ORO. We can relate KSP directly to the molar solubility S, which is the number of moles of the salt that dissolve in 1 liter of water to form a saturated solution. For base SO, if S moles dissolve per liter, then in the saturated solution, base SO and SORO equal SA. Knowing KSP allows us to calculate the molar solubility SOUS for BiSORO S equal is from 1.1 and 0.05 penta-U equal low. This confirms it's sparingly soluble.
So KSP is cycles for 1.1 salts. What's the general formula relating KSP and molar solubility S for a salt with a more complex formula, say MXXY?
Good point. For a general salt with the formula MXXY, which dissociates into excications, mo anions, X0 by C20 XAAC. MXXY X0 XYS plus YA0 by C20 XAA. If the molar solubility is S, then at equilibrium in the saturated solution, mo XS, because each mole of salt gives X moles of the purification. X0 by C20 XAAO equals YS, because each mole of salt gives moles of the anion. Now, substitute these into the KSP expression. KSP max X0 by C20 XAA always XAA. Simplifying this gives the general relationship KSP to XAS. This formula allows you to calculate S if you know KSP or KSP if you know S for any stoichiometry. You might need to solve S KSP X plus Y. KSP is essentially the equilibrium constant for dissolution. We can also define an ionic product, TSP, calculated like KSP, but using the ion concentrations at any moment, not necessarily equilibrium. Comparing QSP to KSP tells us if precipitation will occur. If QSP KSP, the solution is supersaturated. Precipitation will occur until QSP KSP. If QST KSP, the solution is unsaturated, and a more solid can dissolve until QSP KSP. The solution is saturated, and the system is at equilibrium. Textbooks like NCERT provide tables. EOG Table 6.9, listing KSP values for various sparingly soluble salts at standard temperature.
Okay, let's try a calculation using that general formula. Calculate the molar solubility S of a salt A or O's in pure water, given that its KSP is 1.1 then or above.
All right, this tests the general formula with a slightly tricky stoichiometry. First, write the dissociation equilibrium, A arrow plus 3x or AQ. Here, the cation is AO and the anion is XO. From the formula A arrows, we have XO and Y3. If the molar solubility is S, then in the saturated solution, A arrow XS or 2S and XO YS if A arrow is 3S. Now, use the general KSP expression. KSP X over L, X over A goes X over A. Substitute the concentrations in terms of S. KSP 2S or 3S square. Be careful with the powers. KSP 4S or for 107S, we are given KSP 1.1 upon 2082. So 108S is 1.1 on 10 arrows. So 108S go. Now solve for S first, divide by 108. So 1 on 10, 1 and 0.185, iron to 1. To find S, take the fifth root. S 1.01 at 5, 215. This comes out very close to S 1.0 out at how 1 or well. This type of problem, correctly applying the KSP to XO relationship for different stoichiometries is very common.
Got it. That requires careful calculation. Now, how does the common ion effect apply to the solubility of these sparingly soluble salts? I imagine adding a common ion would make them even less soluble.
Your intuition is exactly right. The common ion effect significantly impacts solubility, and just as with weak electrolytes, it acts according to Le Chatelier's principle. If you add a soluble salt that contains an ion common to the sparingly soluble salt already present in its saturated solution, the equilibrium will shift to the left, causing more of the sparingly soluble salt to precipitate out, thus decreasing its molar solubility. Consider silver chloride, AgClS, AgYAQ, plus ClIFY. If you add, say, sodium chloride, NaCl, which is soluble and provides clay ions, you are increasing the concentration of the common ion sol. The equilibrium shifts left to consume some of the added clay, forming more solid AgCl. The result is that less AgCl can remain dissolved in the presence of the added NaCl compared to its solubility in pure water. This effect is used practically. For instance, sometimes NaCl is precipitated from saturated solutions by bubbling HCl gas through it, increasing talco. It's also crucial in gravimetric analysis, where you might add excess common ion to ensure essentially complete precipitation of the ion you're trying to quantify.
Could we do a calculation example showing this effect, like calculate the molar solubility of nickels 2 hydroxide NaOH in a 0.11 OH solution? We know its KSP is 2.0 within NOA.
Excellent example. Let's see how the common ion, OHO, from NaOH affects NeOH solubility. The equilibrium is NeOH plus 2OX. KSP NeOO equals 2.0 to 10 narrow. Let S be the molar solubility of NeOHO in the 0.1 mmOH solution. The concentration of Ne coming from the dissolved NaOH will be S, so Ne S. The concentration of OH comes from two sources, the dissolved NaOH, which contributes 2S, and the added NaOH, which contributes 0.9 m, so the total OH 0.1 O plus 2S. Now substitute these into the KSP expression, KSP S, as 0.0 plus 2S between 0.0 is 10. Here's where we make an approximation based on the common ion effect. Since KSP is very small and we have a significant initial concentration of OH, 0.90, we expect the solubility S to be very small. If S is very small, then 2S will likely be negligible compared to 0.90, so we approximate 0.0 plus 2S, 0.10. Our KSP equation simplifies to S 0.0, F then 0.1, S 0.0, S 2.0, it's N1, S 0.01, S 2.01, S 2.0, 2.0, 10 they're wrong. Now compare this solubility, 2.0 at 10 to the solubility of NeOH in pure water. In pure water, KSP nu always 2S equals 4SM, so 4S equals 2.013 which gives S as 7.9 L TED M. The solubility in 0.1 NaOA and NaOH 2.0 to 10 OA is vastly lower than in pure water, 7.9 to 10 RM, about 40 million times less soluble. This dramatically illustrates how the common ion effect suppresses solubility.
That's a huge difference. Finally, does pH affect the solubility of salts?
Yes, it does, particularly for salts where the anion is the conjugate base of a weak acid. Consider a salt like calcium carbonate or calcium phosphate. The anions, carbonate and phosphate, are conjugate bases of weak acids, HCO and HBO respectively. If you lowered the pH, increase the H concentration, these anions will react with the H ions, COs plus HEOR plus HHBOR, and further pregnate is possible. This reaction effectively removes the free anion, or PORO, from the solution. According to Le Chatelier's principle applied to the solubility equilibrium, for example, COR, decreasing the concentration of the carbonate ion will shift the equilibrium to the right, causing more of the solid salt to dissolve to try and replenish the carbonate ions. Therefore, the solubility of salts containing anions of weak acids generally increases as the pH decreases, becomes more acidic. This is why, for example, tooth enamel, mainly calcium hydroxyapatite, a phosphate salt, dissolves more readily in acidic conditions created by bacteria in the mouth, leading to cavities. Conversely, these salts are less soluble in neutral or basic solutions. Salts with anions of strong acids, like Cla from AgCl, are generally unaffected by pH changes.
Wow, Tudor, what an incredible and comprehensive journey through the world of equilibrium. We've really covered everything from simple phase changes right up to complex biochemical systems and solubility. It really does seem to govern so much in chemistry.
Indeed, it does. We started by defining equilibrium not as something static, but as that dynamic state where opposing rates become equal. We saw how this applies to physical processes like evaporation, melting, and dissolving. Then we delved into chemical equilibrium, introducing the crucial law of chemical equilibrium and the equilibrium constants, Kc and Kpf. We saw how their magnitude helps predict the extent of a reaction.
And then we learned about Le Chatelier's principle. That's such a fundamental tool, isn't it, for predicting how systems respond to changes in concentration, pressure, and importantly, temperature. And the key point about catalysts, they speed things up, get you to equilibrium faster, but they don't actually change where that equilibrium lies.
Exactly. And following that, we ventured into the vast world of ionic equilibrium. We clarified the different concepts of acids and bases, Arrhenius, Brønsted-Lowry, and Lewis. We grasped the pH scale and how to calculate it, especially for weak acids and bases, using their ionization constants, Ka and Kk. We also covered the vital relationship between conjugate acid-base pairs, Ka, Kw, the common ion effect, the fascinating nature of buffer solutions and how they work using the Henderson-Hasselbalch equation, and finally, the principles governing the solubility of sparingly soluble salts with KSP.
It's amazing how these concepts connect. This knowledge isn't just for passing exams, is it? It really helps in understanding the chemical world around us, from, industrial processes to how our own bodies function.
Precisely. Understanding equilibrium gives you a powerful lens through which to view and predict chemical behavior everywhere. Now, for all our dedicated students, especially those aiming for JEE and NEET, here's your final action point from this deep dive. Revise these concepts and definitions again thoroughly before your exams. Make sure you understand the definitions, the key formulas, and the principles like Le Chatelier's.
Yes, and don't just memorize. Practice past year questions based on this topic. Work through as many numerical problems as you can involving KC, KP, pH, KKB, KAP, KSP, and buffer calculations. The more you apply these principles, the clearer and more intuitive they'll become.
Absolutely critical advice. Practice is key. And remember, if you encounter difficulties or have lingering doubts while studying this chapter, please reach out for clarification. Don't let small confusions grow. Keep exploring, keep questioning, and keep deep diving into the fascinating world of chemistry. Good luck with your preparation.